All right, line A1, learning task number 20. We are going to go and take a look at power factor. And it's our final line out of A1. Now, our next learning set module is going to be our A4. That's going to be very similar. We're going to use a lot of content. But this is our final one out of A1. And after this, we are going to go and have a test on what we have covered so far. So let's get into this. This one kind of just uses all the theory that we've covered so far. Inductance, capacitance, angles, all of that is going to get combined together into this final lesson over here where we're going to describe the factors that go and affect power factor. And power factor is going to go and be basically how good a system itself is going to go and be. We did talk earlier on about this other type of triangle. We called this thing the power triangle that had got the volt amperes on the one side, we had the bars on the other side, and we had the watts on the other side. Always everything that is truly resistive, that dissipates its current as heat, is going to go along the x-axis here where we've got the watts. All of our bars are going to be a reactive. It could be XL or it could be XC, and all of our VA is just going to be the vector sum of this amount of power and this amount of power together that we are going to go and have. It's going to be our system capacity. We are going to go and use this VA, and we're going to go and take a ratio of our watts to our VA, the amount of useful work to the total amount that we're dumping in the system to do the watts and the bars. That's what our VA is. We take that ratio, that is going to go and give us our power factor that we're going to look at. Let's start with a real simple analysis. The first one that we have over here is just going to be a practical inductive AC circuit that we would have. We know that all inductors are going to be made out of wire, which means that they're going to go and have true physical resistance, right? R is equal to K times L over top of CMA. It's going to be impossible for us to go and break them apart physically into the inductive component and the resistive component, but what we'll do when we're drawing them is we will group them, just like what's shown inside of here. We'll draw a dotted line around here. That dotted line around here represents the XL, the inductive reactance, as well as it represents the resistive. Overall, we should go have a Z that we are going to go and have from both of these. In fact, if I want to go and find the Z, I could go and take my XL and my R, and I could just go and add them together. Remember how we did this before? We said we'll treat our XL triangles like they're going up. So I'm just going to go and take 67.5 and 117. 67.5, I'm in polar mode, plus I117, which is going to go and give me a value of error over here. What did I punch in wrong there? Try that again. 67.5 plus, oh, I hit the angle there, didn't I? I117. Which gets me out to a Z, a total impedance of this coil. That would be 135 ohms, and it would be at a angle of 60 degrees. So 135 ohm Z at 60 degrees for my angle off of this one. Because it is an inductive type of system, we know that this inductive type of system is going to have a lagging power factor. Now, if it were purely inductive, if we could somehow get rid of all the copper wire resistance and only have the inductance inside of there, we would be lagging at a true 90 degrees. Conversely, if we could go and get rid of all the inductance and only have the resistance, we would be at 0 degrees. But we know that because we have both of them in there, it has to be at something in between there. You remember what we just did there with that calculator where we added these two things up? What we see over here is a 60-degree angle. There's something fantastic about the 60 degrees that we have off of this. That is that the 60 degrees is going to correspond to what my actual lag is going to go and be. Look at this. If we measure, this is 90, right at the peak over here that we would have. And if that's 90, this is a third of the way in from that 90 there that we would be looking for this roughly. This thing should be crossing, my current should be crossing over there at a 60 degree. It's a poorly drawn circuit. It doesn't truly go and show it. But what we see is because we have got this, instead of crossing at the 90 degree with our current, which is what we would have in a regular inductive circuit, because we're crossing at the 60, that means that we have got more time that we are going to be taking power from the supply, and we're only really delivering just this little bit, right? If we cut the tip off of each of these posts over here, we could go and dump them into these ones, that shows us the amount of shuttle power that's going back and forth, which means that overall the circuit is accomplishing true real work. Well, that makes sense because we have got resistance that is going to be inside of that circuit, right? 67.5 ohms of resistance that we have. There's another cool thing that we see about this one, anytime that we've got a practical circuit, and that is that I am no longer going to be symmetrical about my x-axis over here. This point is going to stay the same. Where I cross, where my current and my voltage, it still is going to cross right over here, and then it creates a power waveform. My power waveform will still be double my actual waveform that I have for my voltage, but it's now been shifted up. And the reason it's shifted up is because this current over here has gone and shifted over. I'm going to highlight over top of these because what's fun with this pen over here is that I can actually pick up and move some of these components. This over here would be a truly, purely resistive circuit. If I have that green line right over there, that would be a truly resistive. If I go more and more inductive, what starts to happen is it starts to go move over. If I would increase the amount of inductance, it would move over even further until eventually I would get that thing through to the point where it would be at that 90 degrees, which would be the maximum theoretical inductance. We'll never achieve it, but we can get pretty dang close to those things. So I see that my current, once again, starting from here at resistance, as I go into inductance, it's just pushing the current back further along that axis. What's happening as well from that current being pushed back along the axis is that my power waveform is being dropped. Let's see if I can grab this one. Sometimes it grabs both lines at the same time. It's highly annoying, but we'll see. It grabbed the current one. Disregard the fact that the green line is moving. We'll just take a look at this one over here. Normally, I would go and have, if I had something that was purely inductive, I would see that all of my power would be whatever I'm taking in would be what I'm sending back. Taking in, sending back. That's going to be my reactive power. What does it look like for something that is going to be purely resistive? Well, if we go to something that's purely resistive, what we saw was that our power was all up above that x-axis. You would see every single little bit of it up above the x-axis, and it was going to go and shift over a little bit like that. So that we had these little drops right over here and over here. You can go back a couple of learning tasks, you can find where we start to look at power, but you'll see that that power waveform would all be in the positive realm over here. As we move into a more inductive type of system, all that's happening is that my positive power is moving down and across until eventually it would get to the point where it would be 50-50 across at a theoretical type of inductor. It's just shifting. That's all that stuff is happening. And if something is shifting, the great news is we can usually find some way to go and shift something back. How do we shift inductance? Well, we're going to go and get to use capacitance. So we can shift inductance back, and we can actually start putting everything back to the way it was supposed to go and be. That's one of the beautiful things, that we can make the system right once again. We will do that. That is going to come up in our A4. Just be forewarned that we have to know all this stuff about inductance and capacitance so that we're then able to go and do that shift back properly. Okay, let's take a look at this one. This over here is going to be my impedance triangle. My impedance triangle is going to be a vector representation of my values that I have inside of here. I've got my resistance. This is for that same circuit that we have over here. I've got my resistance, which is always, always, always going to be graphed along the x-axis. And I've got my reactance, which is going to be graphed along the y-axis. Either it's going to be XL going up, or it might be my XC going back down. But it's going to be one or the other, and we're going to graph it along there. Ultimately, whatever I have in here for my resistance and my reactance, my net values, will then go and give me that impedance. You can go and find these values through Pythagoras. You can find them all through using SOHCAHTOA, or you can find them through the calculator the way that we did before by just punching them in. Punch them in as either J operators or I operators in the calculator, or 67.5 at angle 0 plus 117 at angle 90 degrees. Phasor representations of the voltage for this can be done as well. So our impedance is going to be vector because it's not going to be rotating. Impedance doesn't go and change. It's just going to be magnitude and direction. Our voltage is going to be an actual phasor that we are going to go and have. And same with our power, because our power is also going to be rotating. Anytime that I am going to go and draw out a triangle, I need to set a reference. And for me to set a reference, I need to find something, some sort of unchangeable component inside of this system. If I look at this system over here, I should see that I've got one component that's the same for everything. It's not voltage because I'm going to drop some volts here, I'm going to drop some volts here. That's not going to make sense. What is going to be common through the whole thing is my current. Whatever amount of current that travels through this inductor is going to have to go and travel through my resistor over here. And we know that when current travels through a resistance, it is seen as being in phase with that current. So I'm going to start by putting my current down as my first vector. Now, current is supposed to have closed arrowheads. There are vector conventions that you're going to cover, particularly in the third year where you do a lot more vector analysis. But one of those is that voltage has got open arrowheads and current has got closed arrowheads. They've just got a couple of errors on here because they're showing all the vectors with closed arrowheads, but they should have some that are going to be open off of here. So I start with my current. Once I have my current, I then go and say, well, my voltage over top of my resistor is going to be in phase with my current, right? Current and voltage are always in phase for a resistor. So I draw my voltage vector over top of that. I'm also going to go and draw then my inductance vector at 90 degrees to that because it's going to have to be in phase with its XL. What we're going to note is happening is we're getting to that point of having all these similar triangles. We talked about that at the very beginning, that we can have multiple similar triangles that all have the same angles, and we're able to like scale and jump around kind of from one triangle to the next. We see that inside of here, that I'm just copying this triangle, but I'm changing it now into my volts. We can also do one more thing where we can go and change it into our power at that point. This is also fantastic. If I change it into power, it's going to be the same phase angles that I'm going to go and have. Let's finish the solve for this one. The solve isn't shown inside of here, but we're going to go and do the solve, and we're going to go and put values onto the sides of each of these triangles because it helps to solidify what exactly is going on inside of here. The first thing that we are going to solve for is we are going to solve for our impedance. Now, we did that through our calculator, right? We punched these things in, 67.5, that's my X, plus a J operator, or a Y, of 117. That was my XL that I had off of my coil, and we found that it brought us to a value of 135 at an angle of 60 degrees. So we're going to start with that value over there, Z. 130, well, let me draw that triangle because it's actually taller than it is wide. $135. This is 67.5. This is 117 over here. The next thing that I'm going to ask you about is this AC supply. How good is that AC supply's eyeballs? Well, it doesn't have any eyeballs. It's a freaking AC supply, which means that it doesn't actually see what it's connected to. All that it knows is that at its terminals, it has an opposition to current flow. What is that opposition? It's no different than me riding my bike up the hill in the wind. All I know is I got the vector sum, and that's all that my supply is going to go and see and overcome. So it's going to go and have this 135 ohms that it needs to go and overcome. Let's give this thing a voltage value of 120 volts. They don't give us any voltages in here, I don't think. Let me just double check, but you'll see. Yeah, they don't give us any volts. Perfect. Then we're not going to go and cross any of their calculations. So I've got this 120 volt supply that has got no idea what it's connected to. All that it knows that it's connected to is something that is giving it 135 ohms of opposition. It doesn't even know how much of that opposition is going to be from my VARs, my XL, versus how much of it's going to be coming from my resistance. It just sees 135. So it's going to deliver current based on that 135. Let's just be a source over here, and we're going to say I is equal to E, 120 volts, divided by my R, 135 ohm Z. And that's going to tell me the total amount of current that this thing is going to go and dump through that circuit. Clear that. 120 divided by 135, which gets me to a value of 0.88888888. In other words, we're going to just have we're going to call this thing, we're going to round it to 0.889 of current that we will have going through our system. Lovely. 0.889 amps. If we have got 0.889 amps going through here, we can go and solve a few other things. Let's take a look at this. If I have got 0.889 traveling through here, that's going to allow me to go and establish a value of voltage. V is equal to I times R, right? So if I take 0.889 multiplied by 67.5, that's going to tell me exactly how many volts I'll drop across there. Let's go and do that. Take that value times 67.5 equals a grand total of 60 volts that I'm going to be dropping across there. We'll write that in over here, 60 volts over here. How many volts am I dropping across here? Well, our gut would be to say we got 120 volts, we're dropping 60 volts over here, and that we must have 60 over there, but you got to remember that these are out of phase. They're going to go and have similar triangles. So we have to go and calculate it either off of a triangle. We could go and create a triangle that's going to be 120 volts, that's my supply, over top of 60 volts that I'm going to be dropping, 60 volts that I'm going to be dropping across my resistance, and then figure the rest out through trig or Pythagoras, whichever we want. Or we can just take that same current and just dump it through this reactance that I'm going to have over here. That's what I'm going to go and do. So I'm just going to go and just divide by 67.5. I'm just dividing by that 67.5 back out to get back to my original unrounded current. So we've got our unrounded current. We're going to multiply that by 117. Brings me out to a value of 104 volts that I'm going to go and drop across here. 104 volts. Once again, looking at these two values, it looks like we should have a source of 164, but remember that they're out of phase with each other, which is why we're going to add up to 120 volts. 104. 104 over here. If you want to go and verify this, just punch them in. Put in 60 and 104, and we'll see if that thing is going to go and work out. Try that. We'll put it into angles. 60 angle 0 plus 104 angle 90 equals a value of 120.06. So a little bit of rounding inside there, but nothing terrible. At an angle of, would you look at that? It matches 60 degrees over here. Lovely. So our triangles match up. Right? We got 60-degree angle, so 60 volts that we have across the bottom over there as well. Do we have any other triangles that we can go and match out of this thing as well? Why, yes, we do. We have got our power triangle, and our power triangle is going to look the exact same. We are going to go and have our VA. We are going to go and have our VARs. And we are going to go and have our watts that we're going to be over here as well. How do we develop these? A couple different ways that we could. We could go and take our current and multiply it by our voltage. If I take my current multiplied by my voltage, that's going to get me VA, right? That's what it is, literally volts times my amps over here. And then I could do the same through here, and I could do the same through here, and that's going to go and get me my watts and my VARs. We might as well, because it's our common one. The other one that you could use is you could go with an I squared times your resistance values that you have that were given over here. It would be a slight bit more accurate because we calculated the voltage values. Or you could go and do your E squared, your voltage values, divided by your R that you have across here. They're all power formulas. Pick one, try one, just give her, see what happens. Let's try this one over here first. We'll do this one. As for my VA, we will go and use the power, watts, is equal to E times I, but we're not looking for watts. We're going to have to do the power formula, which is VA is equal to my E line times my I line. So let's put that in there. 120 times points. We'll just dump it a whole pile of them like that, which gets me out to a value of 106 VA that I'm going to go and have. So I've got a 106 VA. We'll drop that in over here. 6 volt amperes. For this one over here, let's go with I squared multiplied by R for that one, right? We know that watts equals I squared R, but this isn't looking for watts. We're looking for VARs, so instead we're going to change this to the VARs formula, which looks the same. It's the same formula, it's just called VARs now. And it's going to be the current through the resistance over here. Through my reactance over here, and my resistance, in this case, it's going to be a XL. right, that we will have. So we'll go 0.889 squared multiplied by 117. 0.8889 squared multiplied by 117, which is my XL value, which gets me out to a value of 92.44. So that means that for my bars, we are at 92.44 bars. Makes sense, right? If we take a look at this, the hypotenuse is larger than this side of the triangle. Last one that we're going to have over here, we'll work with our last power formula that we just mentioned. W is equal to E squared over top of R. In this case, we're able to go and use that one as is because we're looking for true active watts. Sorry, I keep pointing to the wrong one, but we're going for the watts off this. So E squared is going to be 60 volts divided by my R of 67.5. 60 squared divided by 67.5, which gets me out to a value of 53.3. So this last one over here is going to be 53.3 watts. Once again, how would I check this? Well, the easy way to check it would just be punching your watts and your bars, and if my watts and my bars line up to become a 60-degree angle with a 106 VA, I know that all of these calcs must be good to go. Let's try it. We will go and take, I guess I could left that in there, 53.3 plus, and we're going to use this one as a J operator, 92.44. So plus I, 92.44, and that's going to equal out a value of 106.7 at an angle of 60 degrees. A little bit of rounding error as we see inside of these always, because we did have a little bit of rounding as we went along. But we see that overall we are back to where we need to be. We have proved that these triangles all have got the exact same ratios. The similar triangles come through for us. The final thing that I would go and look for inside of this circuit, so I'm just going to go and write my VAs over here. Just do that. 106 VA. I'm going to go and write my watts up over here. 53.3 watts. I'm going to go and write my bars down here. 92.44 bars. L. It's an inductive type of circuit that I have over here. The very last thing that I could go and look for off of this circuit is going to be this thing that's going to be referred to as my power factor. Oh man, what did I just do there? Let's go back to that one there. Is going to be my power factor, and power factor is just going to be how efficient is this circuit at doing what it needs to do at a bare minimum without doing a bunch of other stuff that it doesn't need to go and do, namely provide all of that VARs type of stuff if we don't need it. So the way we determine that is we just take a ratio of my total watts over top of my VA. Let's go and do that. 53.3 watts divided by 106 VA that I'm going to go and have over here. Eli, get off of there. What are you doing? Eli, no. That's right. He's attacking the TV right now because it's got all the inking going on in it. That's highly exciting. Back to this one over here. What is this going to be? Well, we'll just take that as a percentage. 53.3 divided by 106. My watts divided by my VA, which gets me to a 50% that I am going to go and have for this thing. That's not very good, that I'm only using 50% power factor off of this one. Another thing that we can do with that power factor is we can go and find the power factor by taking the cosine of our angle. What is cosine? Cosine is simply our adjacent over our top of our hypotenuse, right? That is what the cosine is. Adjacent is our watts. Hypotenuse is our VA. The exact same thing. It's just taking 53.3. So if I know my circuit angle, which we calculated before, it was a 60-degree circuit, I can just take cos 60, which would give me 0.5 for this one as well. The last thing that I should point out is if power factor is equal to my watts over top of my VA, which is also equal to my cos of my angle, if I would therefore go and take the inverse cos of my power factor, that should give me my angle, right? So if I go cos -1 of my power factor. That should get me theta over there. Let's try it. We got a 50% power factor. So inverse cosine, second inverse cosine of 0.5 of my power factor, 50% power factor, is equal to, would you look at that? It is 60 full degrees that we have for this one. Lovely. Okay, that is power factor. Power factor is just going to be the ratio of our watts to our VA. Now, they're going to go and give you a couple more examples that they're going to ask you about, where they're going to go and say, hey, we got apparent power, which is what our VA is. We've got watts, which is our true useful work. Find me my power factor. And at times, they can even go and say, look, I haven't given you your VA, but if I give you your bars, and if I give you your watts, you should be able to either go and use tangent to go and create an angle, or you should be able to just punch those two values together into your calculator to get a value in an angle, and then that value is going to be your total VA, and the angle obviously would go and be whatever the circuit angle itself is going to be. Go through those 4 examples, then knock off that self-test. You get self-test number 20. It doesn't have a lot of questions, but they do take a couple of components. Get used to doing these larger, more complicated, or more comprehensive type of calculations. All right, that covers off our line A1.